Now let us discuss the ratio and root tests. Many of you have probably seen these before, but we are now going to prove that these work. So this is theorem 1. So this is the root test. So let's let an be a sequence of real numbers, and let's let R be a lim sup as n goes to infinity, not a limit, a lim sup, which is good because remember the lim sup is guaranteed to exist. Might be plus or minus infinity, but it is at least guaranteed to exist. Then what you do is you take n, you take the absolute value, and then you take the nth root. You need that absolute value because, square root, fourth root, sixth root of a negative number doesn't exist. But if you take an absolute value, this works fine. Then there are two things. First, this is part A of the theorem. If R is less than 1, then the series, sum from n equals 1 to infinity, and that converges, and better than n converges, it converges absolutely. And then part B is that if R is greater than 1, then the series diverges. And let us go ahead and prove this. Let's look at part A first. Part A is really the interesting part. So let's let X satisfy. X is bigger than R but less than 1. And nature of the real numbers, X has to exist. So our limit as n goes to infinity is R, so there is an n. So our limit is getting, as little n goes to infinity, this supremum is getting closer and closer to R. And that means that eventually your limit, it's close enough to R, it's less than X. And we might as well dispense with this supremum, just say that an to the 1 over n is less than x. And this is by the nature of limits. If you want to look up a precise reference, that would be corollary 1.3.19b. All right, then but this series, the sum from n equals 1 to infinity absolute x to the n converges, and that That is proposition 1.4.4. So by the comparison test, so notice that this up here means that x to the n is greater than, and take both sides to the nth power, absolute value of a sub n. So by the comparison test, the geometric series sum of x to the n converges, and so also must converge the sum of the a sub n's. And remember, that's what we mean by an converges absolutely. And so that completes the proof of part A. We've seen that if R is less than 1, then our series converges. So now let's move on to part B. So part B, if R is greater than 1, then again by corollary 1.3.19b, there is a big N natural number such that if n is bigger than big N, then the supremum over k bigger than or equal to n, absolute value of ak to the 1 over k, is at least 1. And in this case, I can't get rid of the supremum. We aren't guaranteed that all the AKs are bigger than 1. We're just guaranteed for some of them. So, since the limit supreme, now since this supremum is a decreasing function, the supremum of k is bigger than n is decreasing, we can actually get rid of this qualifier. We can just replace it by n, any natural number, because if n is less than or big N, well, your supremum over k bigger than and little n is less than your supremum over k bigger than big N. So this is true for all n. So if n is a natural number, then there is a k bigger than n such that absolute value of ak to the 1 over k is at least 1, then raising both sides to the kth power, ak is at least 1. And why don't I go ahead and subtract 0 inside there. And then if you think through exactly the epsilon delta definition of limit, so it is not true that limit as k goes to infinity, ak equals 0. If that was true, then there would have to be some n where ak is within 1 of 0, within epsilon of 0 for any epsilon, within 1 of 0, within a half 0, whatever, for all k bigger than n, and that's not true. There's always a k where ak is at least 1 unit away from 0. So then our series diverges. Now let's have an example. So recall that this series converges and this series diverges. So we must have that lim sup n goes to infinity, or an 1 over n to the 1 over n. That has to be, that can't be any bigger than 1. If it was bigger than 1, then this series would diverge. And it also can't be any less than 1, because if it was less than 1, then the series without the negative ones would converge. So we've got lim sup n goes to infinity of an to the 1 over n equals 1. So that can't mean, so in this case, our lim sup's 1. And we've just seen an example where the lim sup is 1 and the series converges. Another example where the lim sup is 1 and the series diverges. So your series can converge or it can diverge. So if your lim sup is 1, the root test gives you no information. You can't even rule out the case where it converges absolutely. So here's another example. Let's let an be 1 over n squared. And the series sum of 1 over n squared, that thing converges, and because everything is positive, it converges absolutely. And lim sup 1 over n squared to the 1 over n, that's the lim sup as n goes to infinity, 1 over n to the power of 1 over n, whole quantity squared. And you can you can prove that you can move squares into and out of limits. And we saw before that this limit is indeed 1. So, or rather, 1 squared is 1. So lim sup n of an to the 1 over n can also mean that your series converges absolutely. So now let us talk about the ratio test. So let's let n be a series of real numbers, and let's assume that this limit an plus 1 over an take absolute values that equals some real number r, and it exists. Now, remember, in the root test, we didn't have to do any of this assuming things exist. We could take a limit supremum, which we know exists. In this case, we need to assume that the thing exists. So we have to assume that it exists. And then the conclusions are pretty much the same as in the root test. If r is less than 1, the series converges. And if r is bigger than 1, the series diverges. And let's go ahead and prove this. So, if r is less than 1, we're going to do exactly the thing we did before. We're going to pick a number x that is between r and 1. N is such that if n is bigger than, little n is bigger than n, then an plus 1 over an is less than x. So if little n is bigger than big N, then absolute value of an, it's at most absolute value of a big N times x to the minus n times little x to the n. That's x to the n minus n because you go n steps out. You go little n minus n steps outwards. So that some constant doesn't depend on our little n times x to the n. And our series, geometric series, you can pull constants out of series. You just pull the constant out of each partial sum, and then it sort of only matters whether what's left converges, which it does. It's a geometric series. So our sum of and converges by the comparison test. just as with the root test, if your limit exists and is 1, the series is inconclusive, so we won't rehash those examples. You can go back and look at the examples from the first part of this lecture and see they all have ratio 1 or +1 or -1 in the limit. So I will give you a different example. So let's let an be 1/1/5 to the n if n is even, and 1/3 to the n if n is odd. So our sequence of ANs is we've got 1/3, 1/25, 1/27, 1/625, which is 5 to the 4th, 1/3 to the 5th is 243, and so on and so forth. And you'll notice that our ratio, it's pretty small, then it's about 1, then it's pretty small again, then it's bigger than 1. And so I'll put down AN plus 1 over AN. You can work out what this is. It's 5 to the -n minus 1 over 3 to the n. 3 to the minus n is 1/5 times 3/5 to the n if n is odd, and AN plus 1 over AN is 3 to the -n minus 1 over 5 to the -n is 1/3 times 5/3 to the n, which you'll notice goes to infinity if n is even, and this one converges to 0. So our ratio, our ratio does not exist. So the root test, so the ratio test doesn't tell us a thing about what to do with this series, or, well, the series you get by summing these ANs. But the nth root of a to the n is 1/5 or 1/3. So lim sup. The lim sup is 1/3 is 1. So the series, so the root test tells us the series converges. So there are lots of examples like this where the root ratio test doesn't tell you anything, but the root test does tell you things. The ratio test is sometimes easier to use, but the root test is better. Anytime the ratio test works, the root test will work too. There are lots of series where the root test will give you a definite answer and the ratio test won't. It's just the only reason anyone uses the ratio test is sometimes it's easier to compute the ratio than the root. Now we're going to begin section 1.5. We're going to start discussing countable and countable sets. So here is the definition of a countable set. So this is definition 1.5.1 in your book. So let's let X be a set. And then X is countable if there is a set of natural numbers, not necessarily all of them, but some set of natural numbers, and a bijection, that is a one-to-one and onto function from A to X. So it's countable if there's a bijection from a set of natural numbers onto X, and it is uncountable otherwise. So a couple of examples. So all finite sets are countable. Because finite means you can put a bijection onto some finite, some bounded subset of the natural numbers, or you can just build a function where you just put the elements of your set, you put an order on them. You can do that with finite sets, and then you just let phi of 1 be the first one, phi of 2 be the second one, and eventually you run out. And so we say X is countably infinite if it is countable but not finite. And let's have another example. The integers are countable. And notice that there's more integers than natural numbers. The natural numbers are a subset of the integers. But here's how we do that. We let phi of n be the following piecewise defined function. It is n over 2 if n is even, and it is negative n minus 1 over 2 if n is odd. So then phi of 1 is odd, is 0, phi of 2 is 1, phi of 3 is 3 minus 1 is 2, 2 over 2 is 1, so phi of 3 is negative 1, phi of 4 is 2, phi of 5 is negative 2. So we see, even though our domain is the natural numbers, even though our domain is smaller than the integers in a very meaningful sense, we're eventually going to get to all of them. Another example 1.5 points to C in your book, cut. Is that if X is countable, and Y is a subset of X, then Y is also countable. And we can prove that. Let us also draw a picture. So here are the natural numbers, 1, 2, and then here is our subset A. And then we've got our set X, and our function phi is mapping down. So we've got phi of 2, phi of 4, phi of 5, and then if we pick out a subset of X, say just this one, and just this one, then we can go back to our pre-image here, and then here is a subset B. B is also a subset of the natural numbers. So let's write this out formally, what we've just drawn. Let A be a subset of the natural numbers. Phi a bijection, meaning it's a function that's one-to-one and onto. And we're going to let B be phi inverse of Y. That is the set of all natural numbers in A, such that phi of n is in Y. And notice that this is a subset of A. It's always a subset of the domain of phi. A is a subset of the natural numbers, so B is a subset of the natural numbers. So then phi is a function, if you restrict phi to B, phi maps from B into Y. That is, if n is in B, then phi of n is in Y. Phi is still one-to-one. It's one-to-one on A, and it doesn't stop being one-to-one if you throw out some of the elements. And if Y is in Y, then it's in X, so Y equals phi of A for some A in A. And then by definition, A is in B, so our little y is in phi of B. So phi is on to from B to Y. So phi is a bijection. From B to Y. And B is a subset of A, which means it's a subset of the natural numbers. So y is indeed countable. Now we are going to prove a proposition. The basic idea behind this proposition is, remember, we defined countable in terms of bijective functions, one-to-one and onto. Well, it turns out that you only really need the onto part. You can, if there's a surjective function, it doesn't have to be bijective, that's enough to be countable. So there's a couple ways to put this. They're both useful in different ways. Let A be a set of the natural numbers, and suppose there exists a function f that goes from A to X. Then X is countable. So what we're assuming is that this function f exists. Doesn't always exist. There are uncountable sets for which no such function f exists, but if f exists, then X is countable. And in fact, you don't have to have your domain be in a subset of the natural numbers. Any countable set will do. Let's suppose that, again, we're assuming there exists a function I suppose I didn't actually specify surjective, write down the word surjective in part A, and that's kind of important, so let me write it down. Surjective function g goes from y to x. Then x is countable. So you don't have to use the natural numbers, and you don't need a bijection, you just need a surjection. Let's go ahead and prove this. So part A, if x is in X, let's let F inverse of the singleton set, the set whose only element is X, that's the set of all A in A, such that F of A is in the singleton set X. That means F of A equals X. F is surjective. So if X is in X, then this F inverse of our singleton set, that is not allowed to be the empty set. So let's let B be the set of all B. Actually, let's let G go from X back to A be given by G of X is the smallest of the numbers in be the minimum value of F inverse of the singleton set X. So G of X is the smallest A and A with F of A equaling X. Then let's notice F of G of X equals X for all X in X. And let's let the set B be G of X. That's the subset of A. That's everything you get from G. So G is on to is surjective by definition. And it has to be 1-to-1. If G sent X and Z to the if G sent X and Z to the same number, then this statement could not be true. Then F of G of Z would have to equal F of G of X, so it couldn't be both Z and X. So and F is the inverse of G. That is, F regarded as a function from B to X is the inverse. F regarded as a function on A is a little bit more complicated. So F is a bijection from B to X. F is not necessarily a bijection from A to X, but it is a bijection from B to X. And B is a subset of the natural numbers, so X is countable. All right, and then part B is pretty straightforward. Y is countable. So there exist subset of the natural numbers A and A. Let's call it H from A to Y. That is a bijection. Then we just let F equal G composed with H, so that F of N is G of H of N. Then F, H goes from A to Y, G goes from Y to X, so F goes from A to X. And G is surjective by assumption, H is surjective because it's bijective, and if you compose two surjective functions, you get a surjective function. So F is surjective. So by part A, X is countable.